Section 16.6, Part 2, about surface integral, but this time we'll do surface integral over vector fields, which is also known as flux integrals. Then again, this is 16.7 in a Store's textbook. Before we do surface integral over vector field, when it comes to evaluating these type of integrals, we have to have orientable surfaces. So what's the definition of orientable surfaces? Remember, orientable curves for line integral, they had a direction. So these surfaces gotta have a direction too. So orientable surface is a two-sided surfaces. Okay, it's two-sided surfaces. So um, we have two normal vectors. One is pointing up, the other one is pointing downwards. So n2 is negative of n1 at any given point on the surface. If it is possible to choose a unit normal vector at every such point so that n varies continuously over S, then S is called oriented surface. And the given choice of n provides what? S with an orientation. The bottom line is, look, a surface is called orientable, which is a two-sided surface, is called orientable. If the direction of n doesn't change, what? As you move from one point on the surface to another point. Otherwise, if the direction of the normal vector to the surface changes, then it's not orientable, correct? For instance, two possible orientation for any orientable surfaces. Either the normals are what? Pointing upwards or downwards. So if they point upwards, we say the surface has a positive orientation. If they point downwards, we say the surface has a negative orientation. For a sphere like a basketball, you can either have positive orientation if the normals points what? Outward or inwards. That would be negative orientation. So positive orientation is either upward or outward. Negative orientation is either downward or inward. So in these cases, we have negative orientation, whereas in these two cases, we have what? Positive orientation. And for the surface integral to be evaluated over vector field, you can only do this over what? Orientable surfaces. Meaning the bottom line is it's a two-sided surface which the what? Direction of n does not change as you go from one point on the surface to the next. So orientability implies smoothness when it comes to the surface, but the smoothness does not imply orientable. An example of case B is a what? Surface called Mobius strip, which is one-sided surface, and the orientation changes as you move from one point on the Mobius strip to the other point, and you will always walk on one surface as opposed to two surfaces. So this is an example of what? Smooth surface, but not necessarily orientable. So orientable surface implies smoothness, but smooth surfaces do not necessarily imply orientable surfaces. And orientation serves to specify one of the two sides of the surfaces, yes? So the surface integral over vector field, if F is a continuous vector field defined on an oriented surface, notice we gotta have an oriented surface with the unit normal vector n, so this is a unit normal, that means its magnitude is 1, then the surface integral of f over s is defined as this. It is f dot ds, this is the area vector element, this guy is your vector field, which is the same as plus or minus f dot nds. This is just what? Area element, but this is a scalar. And this guy is the unit what? Normal to the surface. Okay, in other words, ds vector is defined as n times ds. Okay, so when you take the dot product of vector field with unit vector and evaluate it over surface S, and surface S has to be orientable, okay, that means the direction of n should not change, then this is how we evaluate surface integral over vector field. And usually, because this is also known as flux integral, because it shows up in application problems, they denote the flux by the letter phi, correct? So this is like the flux of f across the surface S. What does this say? This says that the surface integral, this formula says the surface integral of a vector field over S equals to the surface integral of its normal component. So we gotta what? Find the normal component of the what? Vector field and evaluate it over S, correct? Now, the plus and minus comes from the fact, positive, if what? The orientation of the surface is positive, negative if the orientation is negative. So plus or minus sign solely depends on the orientation of the surface. You know what I mean by that. That means either the what? Normals are pointing outwards or inwards, or upwards or downwards, then you have to select the proper sign. The special case would be like when z is explicitly expressed in terms of a function of x and y. In that case, what you do, you set this equal to 0. So then you get a capital G function, which is z minus g of xy equals 0. So this is called zero level what? Surface. Is that right? And what you do, you kind of take the gradient of this function, and lo and behold, divided by what? Its magnitude, and that would give you the unit normal vector to the surface S. So this formula, if you have these kind of functions, changes into this form. The flux integral changes into f dot gradient of g dA. What is g? G is the what? Zero level surface. Okay? So now, the question is, why is the normal component of the vector field dotted with what? ds? Well, because if this is the vector field f, and this is the unit normal, and here is a point on the surface S, and this is the angle between these guys, we are always interested in what? In normal component, not the horizontal. Why is that? Because the flux goes across the what? Surface vertically, not horizontally. So therefore, that's why we take what? The dot product of f and unit normal. So NU stands for unit normal vector, which by definition, way back in chapter 12, we decided this is magnitude of f times magnitude of n times cosine of theta. Theta is the angle between f and n, and u is the unit normal vector to s at point P, but unit normal is normal vector divided by its magnitude, correct? So this is basically what we get, and this is basically the reason we dot what? F with n, because we're trying to find the what? Normal component of f uh, on the surface S. In other words, we like to find the projection of F onto the normal vector. So that's where the dot product is coming from. So that would be the component of F, what? Over onto what? Normal vector N. So as I said, this is called flux of F across S. And the surface integral of vector field over S is given by this formula. This is the definition. But remember, I can replace the ds with n ds, but I have to divide the n by its magnitude. So this is your ds. This is like nu, unit normal. But ds, the area element, is defined as unit normal times what? dA. These guys cancel. And lo and behold, here is the nice formula which we use for computational purposes. So the surface integral over a vector field is defined as double integral. Evaluate the what? Express the vector field in terms of parametric equation of the surface, dotted with what? Normal vector, and then replace the dA with whatever these two parameters happens to be. In this case, it was u and v. U and v are generic parameters. Then you would always have du dv or dv du. It doesn't matter. However, there's a special little case here. If z is a function of xy, then as I said, form this equation, set this equation equal to 0, call it capital G, take its gradient, and that would give you the what? Normal vector to the surface. So this formula, in case you have these kind of equations, will give you this formula, plus or minus double integral f dot gradient of g dA. Both of these guys can be used to compute the flux of F across surface S. Notice this formula remains valid if n is 0 at a point on the boundary of the parameter domain. So we will never get to that point. So just to make sure that you understand it. And now we like to see what are the types of fluxes. Flux can be volumetric flux. That's like, water crossing, a surface. Could be gallon per minute, liter per minute, cubic meter per second. It could be mass flux. That's like transporting contaminants, which is mass divided by area times time. Energy flux, that's like energy from the sun, which is energy divided by area times time, and so on and so forth. So those are types of fluxes we're talking about. In our class, we will be talking about volumetric fluxes. Okay, so here it goes. Here's an example. Find the flux of the field, which happens to be this right here, with outward normal. Outward means you have to choose plus sign. When it comes to evaluating the surface integral over vector field, you choose the plus sign. Okay, away from the z-axis, so that means it's kind of like goes this way. That's your normal vector. Anyways, but the surface is what? Cut from the bottom of this elliptic or circular paraboloid by z is equal to 1. Remember, we have open top. This is the surface. So the top is not closed. It's just cut. It gets to be cut by this horizontal plane, but the top is open. So it's an open bowl. So what we have to do immediately, parameterize this circular, paraboloid. I did it like x, y, x squared plus y squared. So the parametric equation, I said let x be x, y be y, but z be what? X squared plus y squared. Remember, all it takes to parameterize a surface is two parameters. In this case, my parameters happens to be x and y. So take two partials, take the what? Cross product. You're trying to find the normal, right? And now up here, I need to check the direction of n, make sure it what? Points outwards, because remember, when it comes to taking the cross product of two vectors, the order matters. So what you do, if you go this way, you get this. But if you pick a point on the surface and test drive this answer, you will see your normal is pointing inwards towards the center. You want the normal to what? Point outwards. So what you have to do is you have to change the signs. That's why it's crucial to check the direction of the n. When I change the sign, I use the same point. By the way, I chose 1, 1, 2. Where did I get 1, 1, 2? I choose 1 for x, 1 for y. But if you work this out, you get 2 for z. At this point, I drew the what? At point P, I drew the x and y and z axis. And I then did this normal, 2, 2, negative 1. So I went 2, 2, negative 1. So as you can tell, now the normal is pointing out of the surface. So be careful. So I had to check the sign, and I noticed my sign is not correct. So I had to reverse the signs of my normal vector to positive 2x, positive 2y, and negative 1. So it's very crucial to check the direction of the normal before you use it in the computation. So we did that, and then I take the dot product, right? And then lo and behold, I know that what? The projection of the solid is a circle with radius 1. Remember, z was equal to 1 and z was equal to x squared plus y squared. So the intersection of these two surfaces is a curve, which is a circle. So what I did, I switched to what? Polar coordinates. Is that right? So if you take a slice of pizza, r goes from 0 to 1, theta goes from 0 to 2 pi, and the answer is 2 pi. Do you see it? Now, a follow-up to that problem. Same problem, but the follow-up. Now the question is find the flux for the closed surface. So that means now the top is closed. Do you see it? Same problem, but closed top. Is that right? So we put a lid on it. So the question is now what would be the flux? The amount of, let's say, fluid crossing this closed surface, which is a solid. Well, in that case, now you have to parameterize two surfaces. The one we just did, in previous example, example number 1. And now we also have z is equal to 1, which is the top. So now I have to even parameterize this guy, which the way I did it, I said x comma y, but what? Z is fixed, it's 1. Take its what? Cross product, excuse me, of the partial derivatives of r with respect to x and r with respect to y from here. You get this, which is the same as k vector. And it's pointing out, so I'm good to go. Therefore, the surface integral over the top is you dot the vector field with the normal, dA. In this case, dA is dy dx. But you don't have to evaluate this because this guy comes up as a constant. And if you take that constant out, you get double integral dA over r, but this is the area of the circle, which is pi r squared. There's no need to compute this. So you get 2 pi. But remember in the example number 1, we had, what do we have now? We had 2 pi. Here, we also got 2 pi, so 2 pi plus 2 pi gives you 4 pi. In other words, I have to split this, integral into two integrals. And notice both of these guys has a plus sign in front of them. Why is that? Because in both cases, we assumed, or they told us so, we have outward orientation. In other words, The normals are pointing away from the surface, like this. Is that right? So those are the normals. So therefore, both of these guys take plus sign. You all see it? So quick example, application of what line surface integral over vector field. It shows up in heat transfer classes. So here's the temperature at any given point in a substance, excuse me, with conductivity, K is equal to 6.5. That's just a constant. It's determined experimentally. Here's the temperature. Find the rate of the heat flow inwards across the cylinder. Y squared plus z squared is equal to 6, where x goes from what? 0 to 4. Notice I have to use what? Surface integral over the vector field in order to find the rate of the heat flow inwards, what? Across the cylinder. However, by definition, vector field is equal to minus k times gradient of the temperature. This is just a definition from engineering classes or physics classes. So first you have to what? Multiply what? Negative k by gradient of this function to get f. Once you do, you get this guy. Then you have to parameterize the cylinder. So the parameters are x and theta. Then you have to perform this integral. And when you do, notice since the parameters are what? X and theta, so dA is what? dx d theta. So depending on how you what were your parameters, when you parameterize the surface S, then your dA element has to be in terms of those parameters, in this case, dx d theta. When you go through all this, you will end up with 156 units of what? Rate of the flow, what? Inwards across the, let's say this would be so many degrees of Fahrenheit per minute. The next example would be Gauss's law, which applies to any closed surfaces. So if E is the electric field, then this surface integral over the electric field is called electric flux of E through the surface S. One of the important laws of electrostatics is the Gauss's law, which says the net charge, which we denoted what by Q, is what? Enclosed by a closed surface is given by this what? Surface integral over a vector field. In this case, your vector field is electric field. And epsilon 0 is called permittivity of free space, which in SI system, that's International System of Units, is 8.8542 times 10 to the power of negative 12 coulomb square per newtons times what? A meter square. So the next item is example relative to the Gauss's law. It says use Gauss's law to find a charge, that's like what? Electric charge, containing the solid hemisphere, x squared plus y squared, z squared less than or equal to 0, but z is greater than 0. So that means we want the upper half of the sphere. If the electric field is this, okay, so you first you have to parameterize the sphere, remember x is equal to rho sine theta cosine theta, sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. Parameterize it, take their partial with respect to phi and theta, cross product it so you can get what? A normal vector, and then follow the formula, and lo and behold, you get an answer, which is 64 pi over 3. Incidentally, when I took the cross product of what? Partial of r with respect to what? What? What was it? Theta and phi. I got this, but remember this is example of multi-surfaces because you have the bottom of the what? Sphere and the top. Remember, Gauss's law only applies to closed surfaces, so you have to have a closed surface. What is the bottom, you say? Well, it's xy0, right? That is, there is no z component on the floor. So on S2, this is what? Basically, the z component is 0. You take the cross product, you find the normal. The normal is this guy. And then you will find out when you apply the what? Formula for finding the net charge. There is no charge at what? Bottom surface. So therefore, the final answer is 64 with 3 pi plus 0, which is still 64 pi over 3. Do you all see it? And basically the total charge is what? 64 pi over 3. And this is that constant which you have to carry it over. You know, this guy has to be multiplied by your integral. So I would say the final answer is this, not that one, is 64 over 3 pi epsilon 0. Epsilon 0 is permittivity of the free space. I hope this helped a little to clear what exactly surface integral over a vector field does, how do you find it, and what's its application in real life. Thank you.